All right, good morning. Hope you all are doing well. So last time we continue our example here with linked list, and we looked at a insertion algorithm. So we started off here in the beginning when we first started this by creating this, and it was a hard-coded list in this case with 5 nodes. But then we wanted to think about really a generalized insertion algorithm that would not only work with this list as our initial state, but really with any potential list as our initial state. And so the idea with an insertion algorithm is that you have really any possible situation with the initial state of your list. It even could be an empty list for that matter. And we want to take a new node that is not currently in the list and be able to insert it anywhere within that list. So the new node could become the new first node, could become the new last node, could be somewhere in the middle. It really could be anywhere. And so we wanted it to be really a generalized algorithm. And so we started writing that out after our traversal algorithm. And so we first created the new node. Again, in this case, it was with hard-coded data. And then we allowed the user to choose the index number of where the node would be inserted. And then we started the insertion algorithm itself. And so first thing we did was, as we do with many of these algorithms, is we take whatever our looping pointer is going to be, in this case PTR, and make it point at what the head pointer is pointing at. So right now, at the beginning, we know that both PTR and head are either pointing at null pointer or at the first node in the list. And then we broke this out into a couple different cases, right? Because that was going to be convenient when dealing with situations like when the head pointer needs to change. So we said if the index is less than or equal to 0, or the head pointer is pointing at null pointer, then we entered this block here. And so the idea was that either way, right, if either of those two cases were true, the new node was going to become the head of the list, right, meaning the first node in the list. And it didn't really matter, right, in terms of the logic, whether the list was currently empty or whether there already were nodes there, because either way, right, we're saying take the new nodes next and make it point at whatever head is pointing at. And the head could be null or it could be another node. And then make the head pointer point at new node. And those were the only two things we really needed to do if we wanted to insert, right, this new node into the beginning. So unlike the array examples where we talked about things like having a shifting algorithm, right, we don't have to worry about those kind of details here because it's a linked list, and we know that the nodes are not in general all stored together in memory. So all we have to do is update our pointers in the correct way, and now we have that node at the beginning of the list. So that was one major case that could come up, but then we have to think about all the other cases, right? What if the node we want to insert is not going to be at the beginning of the list? So we had this else block to handle all, which we might call the general cases, but all the other cases, right, that aren't covered by what we were doing up here. And this is where looping would come into play. So with the first case, since the new node was going to be at the very beginning, there was no looping. But in general, with all the other cases, we certainly might need to use that pointer PTR and loop that, right, and move that up throughout the list. So, and again, we know we've talked about things like pointer offset notation or pointer arithmetic when we were talking about arrays, different ways of potentially processing the elements of the arrays. Well, here the difference, right, is that we're not dealing with an array. So whereas with pointer arithmetic, we might say things like PTR plus plus, here we have to do that in a little bit of a different way, given that the nodes are not in general stored together in memory. But what we did do is we used that index variable to help us out, because the index number is where the user wanted the new node to be inserted. And so we use that as one of the two things that we checked, right, for the loop conditions. So the loop is going to keep going as long as I is less than index -1. But we also have another condition that we're imposing as well. So in addition to that, to keep going, we also have to, or really the whatever node we're at, its next pointer has to not be pointing at null. Because with an insertion algorithm like this, we also want to think about, well, what's the furthest that we should be able to go? And in this case, the furthest that we would be going would be the last node, right? So we don't want to let PTR get up to null. The furthest it should ever go would be the last node. So we can check that in this case by saying PTR arrow next, right? PTR arrow next not equal to null pointer. So that way it'll never move up to null pointer itself. And then I goes up, and then at the same time, we also move PTR up to the next node within the list. So in this case, there was no body also to this for loop. We just put the semicolon right after the parentheses. Because again, really, you know, the whole point of this loop was to move PTR up. So by the time the loop ends, we just need to make sure that PTR is pointing at that correct node to get us ready for the insertion logic that's going to come right after that. And so the idea was that, as we mentioned last time, is that PTR was actually going to be pointing at the position before where the new node is going to be inserted. And that was going to be very helpful because we know the links only go in one direction. But if we have PTR pointing at the node before, then we have a way to connect that also to the new node, and to connect the new node to the node that comes after the node that PTR is pointing at. So when the for loop ended, we really just had a couple of statements that we needed to do to form those links here. So similar to the case with the head node, we only have two statements here. But new node arrow next equals PTR arrow next, meaning we're going to deal with the new node first. We're going to update that link first because that is still going to use PTR to form that link, right? We still have to use what PTR is currently pointing at in order to form that link. So take new nodes next, make it point at PTR arrow next. And then when that link is formed, then we can say PTR arrow next equals new node. And then after that, we just ran through the traversal algorithm and print everything out again. So that was the idea with the insertion algorithm. The key thing here with the general case was having PTR point at that node that was before the position where we wanted to insert. Because that was going to set us up to doing these two statements here. And again, we mentioned last week also that with some of these algorithms, the order, right, does make a difference in terms of the order that you might update your links in. Because in particular here, when we're updating new node's next pointer, we need to have not yet changed PTR, what PTR's next pointer is pointing at. Because we still need to have PTR pointing at that node in order to be able to refer to the next node. So we did that update statement first, and then we said PTR, right, at that point, PTR arrow next equals new node. And that was going to have the effect of inserting new node in between those two nodes within the list. And now deletion is, some of the general ideas are very similar, because in both cases, right, you're going to a certain position in the list, right, and you're making a change there ultimately, whether you're inserting a new node or whether you're removing one of the nodes that you already have. So deletion algorithm has some similarities, but also some differences compared to the insertion algorithm. And like with the insertion algorithm, we can think in terms of breaking it up into a few different cases. Because with deletion, certainly we want to think about things like, well, what if the list is already empty? because in which case we're not going to be doing anything, right? Because there's not going to be anything to delete. There's also the case where the node that you want to delete might be the first node in the list. And then there's all the other cases where you're deleting a node, but it's not the first node. And so the head pointer won't be changing, right? If we're deleting something other than the first node or the head node. So we'll break it out into a few different cases. But now that we've done this insertion algorithm, we can think about certain things that might be similar with a deletion algorithm compared to the insertion algorithm. Because one of the key things with the insertion algorithm was using that pointer PTR and having that point at the node before the position where you wanted to insert the new node. And you know, and we certainly saw with our update statements here why that was a critical part of it. Now, with on the deletion side, you still have to think about updating pointers, right? Because if you have, for example, node A, node B, and node C, then, and if we want to delete node B, for example, then we still have to connect node A to node C directly. At the same time, we want to use the delete operator to release the memory that was previously being taken up by the node B that in this case would now be disconnected from the list, right? So there's the disconnecting aspect of rearranging the pointers, but then there's also the aspect of deleting, right? And releasing the memory that was taken up by whatever node you're wanting to get rid of that has now been removed from the list. And so just like with the insertion algorithm, we're definitely going to have a looping case. We're going to need something like our pointer PTR to be able to move up to the right spot. And then once we get to the right spot, we can start to think about, well, how are we going to update the, you know, for example, the pointers to simulate that idea of getting rid of the node. And then also, how are we going to release the memory? So we talked about the idea of the pointing at the node before with the insertion algorithm. And that idea will also be helpful here because if we have, for example, node A, node B, node C, and we want to get rid of node B, then one thing that has to happen is we have to connect node A to node C. So if we had the pointer pointing at node A, we would be able to do that. So that part will be similar to the insertion algorithm. What'll be a little bit different here, though, is also this aspect as far as deleting, meaning actually using the delete operator, which we haven't done yet in this project, but using the delete operator to release the memory by that particular node that we're getting rid of. And we'll look at an example here in the Word document, but that's the general idea with the deletion algorithm. So a lot of similarities really to a lot of the major things that came up with the insertion algorithm, but a little bit different also because now, unlike with the insertion algorithm, we have to think about also using the delete operator to physically delete and remove that node from the heap when we are removing it from the list. Okay, so we looked at several examples of this here in the different cases with insertion. And so with deletion now, with deletion, we still have to think about that issue of deleting and updating the pointers. But the idea was, for example, if we wanted to say delete this amber node here, then part of it is at that point then connecting the Steve node directly to the Sarah node, right? So if we're taking that node out, then we want to, or at least one of the things we want to do is just change that link. So now have the Steve node going directly to the Sarah node. So updating the Steve node's next pointer at the same time, also using the delete operator to get rid of the amber node. So that's a big part of what's going to happen with the deletion algorithm here. But then like the insertion algorithm, we also will deal with those situations where we might be changing the head pointer, such as when the first node is the node that we want to get rid of, because in that case, you just want to make sure that we update our head pointer. And then we'll also check for things like if the list is already empty to begin with, because in that case, then there's not going to be anything to do. And so one difference here that's going to come up compared to the insertion algorithm is if we try to follow that same approach of, again, here we were talking about if we wanted to delete this amber node, that we would try to have that pointer PTR point at the node before, meaning the Steve node, because if you had that, then it would be very straightforward in terms of how we could connect the Steve node directly to the Sarah node. Whereas if PTR was up here, then like we discussed with the insertion algorithm, right? And if that's the only pointer that you're working off of, then you don't in general have a way to refer back to the Steve node and then connect it to the Sarah node. So we can think about that approach again of having the pointer one position back. And then that's going to make it to where we can update that next pointer, in this case, connect the Steve node directly to the Sarah node. But at the same time, right, we don't want to just leave the amber node, sort of hanging or dangling in memory. So we're going to want to make sure that we delete that. So there is going to be another pointer involved because we're going to want to have a separate pointer. In this case, that would be pointing directly at the amber node, so we could use the delete command over that. So we will have a second pointer that we can use here to help with that, but that'll be a little bit of a difference compared to the insertion algorithm now that we're also wanting to do things like avoid a memory leak and actually release the memory whenever we do disconnect a node from the list that we've originally formed. So case one, if we want to have a special case for dealing with empty list, there wouldn't be anything to actually do there, but we might display just a short message to the effect of the fact that the list is already empty. Case two would be where the node that we're deleting is the head node. Because then we will need to think about updating the head pointer. That summarizes the general idea of our three different cases here. So empty list case, case two, where the head pointer is going to be changed because the head node's the one we want to delete, and then all the other cases are case three. So case three is where our looping will come into play, and we'll use a couple of pointers here. One is our looping pointer, and then another pointer to actually release the memory when we do disconnect that node from the list. But that's the general idea of our deletion algorithm here. And then just like before, you can use that same index variable, but the index number is going to be used again. That's going to be controlling which node is the one that gets deleted and removed from the list. And then here, so this represents the case where, and we mentioned before that the way that the index variable was handled was that if they entered, for example, a negative number or something like that, we would just treat that as if they entered zero. So else if index is less than or equal to zero, then that represents the case where the head node is going to be deleted. Now here we've already previously checked, right, whether head itself was a null pointer. So if we get here, and this is true, right, then we know that that head is not null. So we know that there's at least one node anyways in the list. But we want to delete that head node. So really, we just want to make sure that the memory itself can be released, and at the same time that we can update the head pointer. The idea being that if this head node is the only node in the list, that's okay. Then that just means that now the list is going to be empty, in which case the end result of this is that head should be pointing at null pointer. Or if it's not empty, and for example, we have node A, node B, node C, and we're deleting node A, well, then node B is now going to become, right, the new head of the list. So one way or another, we just need to make sure that that head pointer gets updated correctly, and that the memory itself can be released. So again, so far we really weren't getting into all those details last week as far as releasing memory, but now we want to start thinking about that. And in fact, another algorithm that we can do after this deletion algorithm, because this deletion algorithm is talking about going into, getting an index number and deleting that one specific node from the list. But at the end of the actual program itself, just like we did before back in chapter 9, when we were dealing with dynamic arrays, we want to think about cleaning up the entire structure, right, from memory. In this case, the entire linked list. So after this deletion algorithm, then we can think about an algorithm that will actually just remove the entire list, right, before the end of the program. But here are things to do: or move the head pointer, right, update the head pointer, and then also release the memory itself. Well, as far as updating the head pointer, one thing we know is that either if this is the only node, then the head pointer's next will be pointing at null pointer. Or if there are other nodes, then the head pointer's next will be pointing at, right, the second node in the list. So either way, that gives us a way in which we can deal with the issue of updating that pointer. At the same time, we want to delete the memory that was, being taken up by the old head node that we're about to delete here. We can think about something like that, because if we say head equals, in this case, head equals head arrow next, that's just saying whatever the head's next pointer is pointing at, now we want head itself to point at that. And again, that could be either null pointer or the address of the next node in the list, if there's already multiple nodes in this list. At the same time, we want to be able to get rid of that first dynamically allocated student object, in this case, that was the old first node in the list. So here we initialize in the beginning PTR to point at head. So we're really just saying delete over that first old node in the list. So we can just really generalize that whole process here. It doesn't really matter if head arrow next was originally pointing at null or whether it was pointing at the second node. Either way, we're just going to move the head pointer up. And then since we already, after the insertion algorithm and all that ended, since we set PTR back to head again, if we say delete PTR down here, then that's also going to be deleting the head node, right? Since we didn't change PTR between there and the delete statement. So that's just going to move the first node. So just clean that up from the heap, and then now we can handle all the other cases. And again, it's always helpful to think about, what we know at each point here. So we know, for example, since we checked this first, if the first if statement was not true, then that means that head was not null. So by the time we get down to here, we know that there's at least one node anyways with this else if. So if that's the case, and then furthermore, index is less than or equal to 0, then we know that we're talking about deleting the first node, which may or may not be the only node in the list. And then down here, right, we're wanting to handle all the other cases where we're deleting a node, but we know since the other two cases above were not true, that we're not deleting the first node. So the idea is that if we make it down to the else case, then we really know that there's actually at least two nodes in the list at a minimum. And the node that we're deleting is not the first node. So at least two nodes, and then the node that we're going to be deleting is not the head node. And so some of this is very similar to the general idea with the insertion algorithm, because you might, if we think back to what we did before, we had that loop. It had the two conditions of index, and in this case, we were looking at PTR arrow next, right, with the loop here for the insertion algorithm. So in many ways, this is going to be similar because the user also is providing an index number to control which node is going to be deleted. But it will be a little bit different here, but we can go ahead and think about doing something similar here. Now, one thing that we also know to be the case, at least from the insertion, when we were doing this as an insertion algorithm, was that when you thought about how far PTR could go, right, in terms of how far up in the list PTR could go, well, we know that our condition said really two things had to be true to keep going. I had to be less than index -1, but again, the user could have entered a really large number for index. But the other thing was that PTR arrow next had to not be equal to null pointer. So in terms of how far you could go, right, with your pointer PTR on your list, the furthest that you could go would be the last node, right? Because you get to the very last node in the list, and at that point, when you check PTR arrow next, it's going to be equal to null. And that's definitely one of two ways to stop the loop here, or at least the way that we stopped it in terms of the insertion algorithm. Because we said that with the insertion algorithm, right, that was the furthest that you would ever want to go, would be the last node. In particular, we wanted to make sure that PTR itself could not get up to null pointer, because the whole idea, right, with the insertion algorithm was that it was going to be pointing at the node before. And so from that, right, the furthest we would want to go would be the last node, because if we wanted to insert the new node as the new last node, then we want to have PTR pointing at the old last node so we can form, right, that link. And in a similar sense, we have to think about the same kind of issues with the deletion algorithm, right? In terms of how far do we want to go? And is that going to be the same as what we did with the insertion algorithm? Well, so if we do the exact same condition with the insertion algorithm as we did with the deletion algorithm, then it would be possible, for example, for the looping pointer PTR to be pointing at the last node. But then we have to think about it, is that really what we want for a deletion algorithm? So in other words, do we ever want the pointer PTR to get all the way up to the last node itself? Certainly, it's possible that we will want to delete the last node, right? So delete the last node and make the original second to last node become the new last node as a result of doing that. Certainly, that's something that might come up, but the question then is, though, where would you want the pointer to be pointing at in that case when you're deleting the original last node or the original tail node from the list structure? But we talked about the issue of having it point at the position before, right? Which is exactly what we do with the insertion algorithm, but there is a little bit of a difference there. Oh. Does it matter if you say PTR arrow next? The difference would be because the short circuit evaluation. So if the first condition that you check is false, then we already know the whole thing is going to be false. Yeah. So that'd be the only difference there. So for example, if we put in a big number for index or something like that, and then we check this and this part was already false, then in that case, we wouldn't check this. Or vice versa, right? So because the user is supposed to ideally, put an appropriate value for index based on the current state of the list. So conversely, if this part here becomes false, then we also don't need to check the right-hand side. So whichever one's on the right-hand side of the AND will not be checked if the expression on the left-hand side is already false because of short circuit evaluation. So, but in that sense, we could really put it, we could really put it either way in terms of the order here. Mm-hmm. Yeah. Now, with the insertion algorithm, the reason why we let it go all the way up to the last node was because of one case that come up was that you wanted to insert the new node as the new last node, meaning coming after the original last node. Here, the furthest, right, in terms of what you might do would be deleting the old last node and then making, as a result, the old second to last node become the new last node in the now smaller list. And so we don't actually really want PTR to get up to the old last node. We really would only want it to get up to the old second to last node, since the pointer is pointing out the position before the node that's actually going to be deleted itself. So what we can do here is just change our logic a little bit to account for that. So PTR arrow next, not equal to null pointer, instead of saying PTR arrow next. So with the insertion algorithm, we were saying furthest that you would go would be the last node in the original list, which is the point where PTR arrow next would be null pointer. Here, we're trying to say really that the furthest that you would go would be the original second to last node, where PTR arrow next would be equal to null pointer. So just going one less, right, at the most compared to the insertion algorithm. Because that is a little bit of a difference between insertion and deletion. So again, with insertion, it's possible that the new node that you're creating is going to come after the original last node, which is why you would want your looping pointer PTR to still be able to go up to the last node. But here, since we're talking about deletion rather than insertion, there's really no situation, right, where PTR should be getting up to the last node itself, since the pointer is always supposed to be at the position before the node that's actually deleted. So the idea being that if PTR were getting up to the last node, that would imply, right, the next thing would be null, but then we wouldn't actually be able to delete anything. So we're going to limit it to the second to last node. But other than that, right, the looping structure is very similar to the insertion, right? Because that's really the major difference. So each loop iteration, PTR gets moved up one position in the list. And so there wasn't a body in this case for the loop. And then we can think about the logic that happens when that loop is finished. So just like with the insertion algorithm, what the loop is doing for us really is getting PTR where we need it to be by the time the loop is finished, getting it to that node before the node to be deleted, so we can update that link. Now, the other side of it was making sure we avoid a memory leak. And so that's why where another pointer can come into play here. So PTR was our looping pointer, but then we'll make another one, PTR2, for example. And so what we can do now that we've already used PTR and moved it up in the list, is we know that PTR is pointing at the node before the node that's going to be deleted. So we can make PTR2 point at the node to be deleted itself. So for example, PTR2, when the loop ends, PTR2 is equal to PTR arrow next. And then we're going to be able to do all the things that we want to do here. So update the pointer, and then also release the memory. So now let's go back to the diagram here for a minute. So now, again, we're assuming here that this amber node is the one that we want to delete. So now we have, assuming that's the one we want to delete. So for example, if the user put in 2 for the index, for deleting index number 2 node or the third node, then so here what we would have is, right, PTR will be pointing at the node before, right, the Steve node. And then we also just did that statement that said PTR2 equals PTR arrow next, meaning that PTR2 would be pointing here at the amber node. And so now what we're going to do, first thing we're going to do before anything else is we're going to update the links, right? So again, we have to always think about the order of doing things here. So in particular, if we try to start by deleting the amber node, then we would have no way to connect the Steve node to the Sarah node, right? Because we still need to be able to use the state of the Amber node's next pointer to get to the Sarah node, right? So we're gonna update that pointer first, and then we can think about releasing the memory of the Amber node. So here, the nice thing is, again, since we have PTR one position back, that's going to give us what we need in terms of updating the pointer. Because really, we really want to say that we want to take, right, this node, right, the Steve node's next pointer, and we need to make it point at whatever the Amber node's next pointer is pointing at. Because the end result is that we want to have the Steve node connected directly to the Sarah node. And so there's a couple of different ways that you can do that based on the pointers that we've already set up here. One way would be, right, for example, PTR arrow next equals PTR2 arrow next, given that PTR2 is now pointing at the Amber node in this case, right, the node that's actually going to be deleted. So we could do it that way since that link has already been formed. Or you could say things like PTR, right? PTR arrow next equals, right? PTR arrow next too. But either of those are going to be okay here, given the pointers that we've set up. But we need to connect that Steve node to the Sarah node. So we're going to do that, and then after that, we're just going to use the delete operator over PTR2, because that's why we had that pointing directly at the Amber node in this case. So just update the link. Again, since it's a single link list, there's the major thing that we have to do is update, in this case, the Steve node's next pointer and make it point right now at the Sarah node. And then once that's been done, once we've updated the link, then we can just safely, right, use the delete operator over PTR2. Because that's going to avoid a memory leak. And then, like we mentioned before back in chapter 9, if there's still going to be a period of time where that pointer is going to exist, then you can also set it to, for example, null pointer to make sure it's not still pointing at that old location on the heap, right? Because we know that you can do that to avoid the problem of having what we call the dangling pointer, where the memory's been released, but then you still leave the pointer sort of dangling and pointing there anyways, even though it's already gone. Well, we can avoid that too by just making it point at null pointer as soon as we do the delete. Okay, so that's really all we need to do, right? So not too many things come after the loop itself, just updating a pointer, right, and then deleting the actual node from memory. Those are the major things that we need to do when that for loop is finished. So either, right, we know the statement's taking the node before, making its next pointer point at the node after the node to be deleted, or right at null pointer if the node to be deleted was the last node in the list to begin with. And then we can actually then think about releasing the memory, right, with the delete statement. Just a few things really that we did here after that after that for loop finished. And again, we saw the loop was similar in many ways to the loop that we use for insertion. It's just a little bit different now with the chaining of the next operator twice or the next pointer twice. And then we just, again, make the node before connect to either the node after or null pointer, and then release that memory. So that's really all we needed to do there. And then like before, if we want, we can do the traversal algorithm again if we want to do another print. After doing the deletion. But so that's our deletion algorithm. And again, you're doing some of these things in your assignment in terms of functions, right? So that'll be the next step is for you to think about how you can also put these in individual functions. But so that's again a deletion algorithm that is going to delete one node. But before the whole program itself ends, you do want to think about memory and making sure that we don't leave things on the heap. So whereas a deletion algorithm is for going in and deleting a specific list, right, to update the overall state of the linked list, we should also have a destroy list type of algorithm that will ensure that the entire linked list is going to be destroyed, at least by the time the program ends anyways. And so what that means really is just a loop, but that loop is going to remove every single node, right? Delete every single node. So we'll do that one here as well. And now the general idea is this one can also work using a couple of different pointers that'll work together. The idea is that we need to, similar to a traversal algorithm, or really a lot of these algorithms, we're going to move up to each node in the list. At the same time, we're going to need to have something that we can use the delete operator over. And So we're going to use a couple of pointers here because we still have to think about the issue of moving up, right? Because we're eventually, in this case, we're definitely going to go through the entire list, right? Unlike the insertion deletion algorithm, in which case we may only, go to a few nodes depending upon which node position where we're going to insert the new node or which node position we're going to delete that node. But here, since we're talking about destroying the entire list, we're certainly going to be going to each node eventually. And so part of it, similar to the traversal algorithm, right, is that we're going to, be doing things like an update statement, but at the same time, we're going to also be deleting the node that's there as well. So we started off here in the beginning by initializing both of these pointers to whatever the head is, meaning both PTR and PTR2, because we're going to need a couple pointers really to do this here in our loop. And so we can start by taking, for example, one of the 2 pointers and go ahead and move that up to the next position within the list. So for example, on the first loop iteration, assuming there's multiple nodes in the list, then after we do PTR2 equals PTR2 arrow next, then now PTR2 is going to be pointing at the second node. But PTR at that point would still be pointing at the first node. So the idea is that we're going to be deleting the nodes in order from the first node to the last node. So PTR2, for example, moves up from the first node, and if that's the only node, then it would be PTR2 would be at null. PTR is still, after this statement here, is still 1 position back. So you could do like delete over the PTR, and then we could update PTR. So the idea is that these two pointers are going up right together essentially. So again, we initialize them both here in the beginning to head. But the key thing was that there's that PTR2 moves up first, right? So for example, if the condition here for the while loop is true, then do the statement PTR2 equals PTR2 arrow next. So wherever that is, either null pointer or the next node, go ahead and move PTR2 up. And then, but by the time we get to here, PTR itself has not been moved up, right? It's still pointing at that original node. So go ahead and use delete over PTR, right? But then right after the delete statement, then we just go ahead and we move PTR up to where PTR2 is. So as we enter each loop iteration, the idea, meaning as we check the condition here and then enter the loop body if the condition's true, right? Every time we do that, we're entering the loop with PTR and PTR2 pointing at the same thing. So by the time, right, again, by the time the loop ends, each loop iteration ends, they're going to be back to pointing at the same thing. So move PTR2 up first, delete whatever PTR is pointing at, and then also move PTR up to where PTR2 is pointing at. And keep doing that until we eventually reach null here. So that's a basic destroy list type algorithm. So that's just going to destroy the entire list. So somewhat similar to traversal in the sense that we set the loop up here similar to how we did the traversal loop condition. But in this case, instead of printing things out, we're actually just wanting to destroy the entire list. So if we go back to that Word document, so the difference now is that instead of just deleting a specific node, we're going to delete all of them. So what we started off here was, again, we really started off with actually making PTR and PTR2 point at what the head pointer is pointing at. So at the beginning, we have all three pointers at this point at the same spot. And then we said that you take one of the two pointers and you move it up first. So the whole idea, for example, if you think about the stages of this algorithm, is we check the condition first, PTR not equal to null pointer, since this has to go throughout the entire list. So the condition is just checking against null pointer. And then the first thing was we said move PTR2 up, right? With PTR2 equals PTR2 arrow next. But we leave PTR hanging back, right, for a short period of time, because then the next statement was delete PTR. Well, so the whole idea is that we've already moved PTR2 up by one, right? So we're not gonna lose, right, the rest of the list here, because we already moved PTR2 up, and then we said delete PTR. Well, so that means that the whole first node is going to be gone, right? So this and this are now gone. And then we ended that loop iteration by then saying, well, that now just go ahead and move PTR up to where PTR2 is. And then on the next loop iteration, same idea. At that point, move PTR2 up first with PTR2 equals PTR2 row next, right? So move it up. PTR is still hanging back for now. And then delete, right? Delete PTR. So delete the node. And of course, that means the whole node, including, right, the memory that was taken up by its next pointer, right? All that's now gone. All that's removed from the heap. And then end the loop iteration by moving, right, by moving PTR up. And then it's just going to keep, right, keep going and keep going in the same fashion, right? So now the loop iteration ends like that. Beginning of the next iteration, move PTR2 up. PTR is still hanging back for now. Delete PTR, so delete, right, this node. So now that's gone. And then end the loop iteration with moving PTR up to PTR2. And then move PTR2 up to here. PTR hangs back, so now delete that node. And then end the loop iteration with moving PTR up. Now at this point, PTR2 is pointing at the last node, right, this Bob node, which is fine. So then we go into the condition still true. Move PTR2 up to null pointer, right? PTR would still be pointing here. So then delete over that node, get rid of it, and then move PTR up. And then the loop would end with, the last loop iteration would end with them both pointing at null pointer. And then you come back up and you check one of the two. We really only have to check one of the two, right? Since the two are ultimately moving up together, right? Meaning that by the end of each loop iteration, they're both going to be pointing at the same thing. So just check one of the 2 pointers. And then if it's null pointer, then just go ahead and stop the loop. So that's the idea, right, with a general destroy list type algorithm. And then, I mean, the only thing from there that you could also think about would be avoiding dangling pointers. Now, when the loop ends, because of the way that this works, we know that, for example, PTR2 and PTR are going to be null pointer one way or another. Now, there's also the issue of the head pointer as well. So the head pointer itself was not changing in the loop, right? But it is something that, you know, we can still think about, given that this is an algorithm that destroys the entire list, right? Releases all the memory that was taken up by all the dynamically allocated, in this case, student objects that were in that list. So now, if the list was initially empty, then that would mean that head was originally pointing at null pointer and the loop didn't actually run at all. But if the list was not empty, then we deleted one or more nodes. And so we know that when the algorithm is finished, all the nodes have been released in terms of being released from the heap area of memory. But there is still the issue of dealing with the head pointer, right? So making sure that we don't have a dangling pointer with the head pointer. Because just like we said in this diagram here, right, we got rid of all these nodes, which is why we moved them all down. And we also know, because of the way that it was set up, that certainly one way or another, by the time that while loop is finished, both PTR and PTR2 are definitely pointing at null, since that was the condition of the loop, and they both move up together, right? By the end of the loop, at least, they both have moved up to wherever the next position is. But that doesn't automatically happen with the head pointer, right? So after the loop is finished, we could also just set the head pointer to null pointer to make sure that we don't have a dangling pointer with the head pointer. Because again, you know, if you don't do that and you just run through the loop and then that's it, well, then you have the situation where the head pointer can still be a dangling pointer. And if there's more things that are going to happen, especially in the program, you know, we don't want to just leave the head pointer pointing at that location on the heap. So we just want to make sure that it would get set to null pointer. So that's one thing that we can do after the loop. But then other than that, that's really all we need to do for this destroy list algorithm. And again, you know, we've been doing this just in main, but you're doing this for your assignment in terms of functions. But that gives you an idea of also the difference, certainly, between the deletion algorithm and the destroy list algorithm, right? So deletion just is talking about one node at a time. Of course, you could call that function repeatedly and, you know, delete multiple nodes over time. But the destroy list is more of like a cleanup, right? Cleanup type function to make sure that it, at least by the end of the program, but really by the time whenever you're done using the list, that all of those nodes are now being released from the heap, right? Making sure that we clean up everything in terms of our data on the heap. So that is the idea behind the deletion algorithm. So now in a second here, we can go ahead. Now that we've done these two new algorithms, we can think about running them. And actually, one more condition we'll do here for the deletion algorithm. So in case the user, for example, puts in a big number for index or something like that, but there's only one node. So we'll do another condition here for case 2, just checking if head arrow next is null pointer. The idea being that if that's the case, then regardless of what happens with index, we're going to just, of course, if there's only one node, then we're saying that we're going to delete that one node. Because the idea with this loop here was this loop was designed to work assuming that there's 2 or more nodes. So we just want to make sure that if there's only one node, then one way or another we run through case 2 logic. So if the index number, for example, is 0 or a negative number, right, that's going to happen. That means delete the first node. But again, if the user puts in a larger value for index, we still can check that through head arrow next, right? So if head arrow next, the head pointer's next pointer is pointing at null pointer, then we know certainly that it's the only node in the list. And so we're still going to run through case 2 logic, because especially with the way that we set this up, right? with our for loop logic here and saying things like PTR arrow next twice, right, where we're chaining the next operator twice. Certainly, if we're going to be saying things like that, then we want to be sure that the only way that we can hit the else block, right, is if in fact there are at least two nodes. Because since we're chaining, especially since we're chaining this twice now, you know, if there was only one node, but we were still able to end up here, then you could have the situation where this part would evaluate to null, right? PTR arrow next, there's only one node and PTR points initially at the head node. Then, you know, PTR arrow next could be null. And then you could be potentially saying null arrow next, which is not allowed, right? Because we can't apply the next pointer to null pointer. So this loop here, again, is really designed to work with two or more nodes, especially since we're chaining the next operator twice with the check here. So that's okay as long as we just make sure that the only way that the else block can be hit is if we know for sure that there's at least two nodes in the list. And it follows that if, you know, if neither head is null nor head arrow next is null, since the last node always points at null pointer, right? If we know that all those things are true, then we also know that there's at least two nodes in the list. So we're okay in that sense with things like chaining, right, the next pointer twice, because we're still only moving up. We still only move PTR up one node at a time in the list. So as long as we start out with at least two nodes, and then we know that it's never going to work out to where the first next is going to return null, and we're saying things like null arrow next. So just a little bit more that we'll say there for case 2, because, you know, again, if they did put a large number for index, then we still have another way of checking that there's only one node by looking at what the value of head arrow next is. Mm-hmm. So case 1, again, for deletion was just null, and then that's 2 cases we'll actually check there for case 2, and then case 3 is the same as before. And then we ran through our traversal here, and then after traversal, we ran through the destroy list algorithm, and then also set head to null. And then the idea was also that, you know, if we tried to do the traversal algorithm again after the destroy list, then nothing, right, should happen because the list should of course be gone. Okay, so we have the original output at the beginning with our 5 nodes, and then last week we did the insertion algorithm. So we'll just do index 2 here. So first we're running through that insertion algorithm from last week where we put that new Dave node in this case at index number 2 as the third node. And then this time when it asks for index number, now it's talking about the node that we're going to delete, right? Since we've already run through the insertion algorithm. So we'll go ahead and delete, let's say, the Amber node here, similar to what we were doing in the Word document, except now we also have this Dave node in here. But we'll go ahead and delete the, let's see, the Amber node, which is this 0, 1, right, 2, and 3, right? So Amber node is the fourth node, then at index number 3. So then it prints them out again. And then, so traversing list after deletion, we still have James, Steve, Dave, and then Sarah, Bob, right? So that Amber node has now been removed or destroyed from the list. And then the idea was after that, we ran through the destroy list algorithm, and then we put the code for traversal again after destroy list. But since the entire list has been destroyed and we set all the pointers like head and PTR, PTR2, for example, we set all those to null. So nothing, in terms of output, nothing happens here, because when we hit the, at this point, when we hit the condition for the while loop, meaning for traversal after doing the destroy list, then it's going to be false immediately. So we don't see any output there. So, which is what we would expect after running through the destroy list. So that's the idea of our deletion and destroy list algorithms, and we can do a few more quick runs here. Okay, we'll do index 2 here again for the insertion. Let's do index 0 for the deletion. So in this case, if we put in index 0, that means delete right the first node, meaning the James node. So now we have Steve, Dave, Amber, right, Sarah, Bob. So meaning it correctly deleted that node. And then again, when we try to do the traversal after destroy list, nothing happens since the pointers are all null at that point. All the nodes have been successfully removed. And in this case, we put 50 for the index. Again, that's much bigger than the number of nodes. But when we look at the printing here of list after deletion, we can see that that last node, the Bob node, right, because that's how we're handling index, right? So the most that we can do, of course, is delete the last node in the list, which is what happened here. And then we, again, we don't have any output when we try to do traversal after running through destroy list. So that's the idea. Again, we've seen now insertion algorithm along with deletion and destroy list. And so we're seeing how a lot of these algorithms work when we have a single linked list where we have pointers going in one direction but not the other. So any questions so far? Okay. So now we'll start looking at binary files, and then after that, we'll come back and we'll look at linked lists some more. In particular, we'll look a little bit at doubly linked list, which you've already seen a little bit with your discussion board from last week. And we'll also eventually see things like how to combine this idea of a binary file potentially with a linked list. And that'll come up in your assignment this week as well. But so when we talk about a binary file, we're talking about really processing a file in its native binary format. So we're very used to working with text type files where we have a file maybe with the extension txt, and maybe each line on the file is storing a name or maybe even a number, right? Anything is possible. And the way that we manage and organize the data is we have delimiter, right? We have some sort of special symbol or character that distinguishes one entry in the file from another, or what you might say one record in the file from another. So for example, we've been using a line return, right? Every time we've been dealing with the file, we've been using a line return to distinguish one value from the other, whether they were words like the boy names and the girl names, right, which you did in one of your assignments, or whether they're storing numbers. Either way, the line return was being used as what we call a delimiter. And now the idea really is that when you use a file in ASCII text mode, which is what we've been doing, you're really ultimately everything is a character, right? Even if we think of it as storing a number, right? So when you read in a line with what we think of as a number and then read it into maybe integer variable, well, there's more that's happening behind the scenes though, right? Because you're really converting that sequence of characters to the corresponding number. And so that's one way of handling data, right, is with text mode, what we call ASCII text mode. But we can also deal with data in its native binary form, right? So in the end, everything is binary, right? Everything is ones and zeros. This is one of the first things that gets talked about in the 260 assembly class, because there you get into all the details about binary and hexadecimal and how all of that works. But we do have the ability to process data in its binary form directly without having to deal with all the abstractions that come about from this idea of an ASCII text file. Because again, just like with many things in a high level language, right, we're doing abstractions, right? We're kind of abstracting and hiding the details when we do that. And another thing is that also when we deal with the file in ASCII text mode, there has to always be some sort of delimiter, which is usually a line return, but I mean, it could be something else. But there has to be some sort of delimiter, because otherwise you would have no way of distinguishing one data value from another, right? We can't just run all the data together, because then how are we going to know what's part of one name or what's part of another name if the file is storing names, or which of the digits, for example, are part of this number versus that number if all the digits are run together. So we have to have those extra characters, right, for things like a line return, because that's how we distinguish things with the ASCII text file. With a binary file, we don't have to do all that. So it's a very different way of thinking about things. But in the end, right, we can still do all the same things that we could do with ASCII text file. So the data is still there, But it does give us some conveniences in terms of how we process that data. So for example, when we think about things like dealing with an array of values, and it could be an array of strings, it could be an array of numbers, whatever value we want. If we're dealing with a text file, then we always have to think about the issue of, well, I got to make sure that I put my line returns in the file, because if I don't write my line returns, then it's all going to be wrong. So we do things like loop through the entire array, write the first value, then write a line return, then write the next value, write another line return, and go and so on and so on. With a binary file though, right, you could write that whole array in one statement, right, one go, right, without having to use a loop. In particular, because we know that all the elements of the array are stored back to back in memory. And we'll see that there are functions that you can use to grab the whole array, right, as one block and just write that whole thing. Or conversely, read an amount of data from the file that corresponds to the size of the array and read that much data from the file and bring it all into the array in one go, right, one statement without having to use a loop. And because we don't have to worry about things like delimiters and the line returns, right? So with the binary file, we can have all the data back to back to back with no delimiters, for example. So that's what's going to make it possible to do things like take an entire array and in one go write the entire array to the binary file, right, without having to loop individually through each location. Or conversely, read all the data from the file and in one go bring it all of it into the correct spots within the array. But we do have to think about things certainly in a very, very different way compared to how we think about them with an ASCII text file. Because everything revolves around the fact that the data is in binary, and everything really revolves around the idea of a byte. So a byte is really a group of 8 binary bits together. So binary itself is a numbering system that consists only of ones and zeros, which is why we also call it base 2. So everything is ones or zeros, but 8 of those ones or zeros together is what we call a byte. And a byte is really the baseline of everything, right? Everything kind of builds off of that size of 8 bits or bytes. Because we've looked at many different memory diagrams, but one thing that we've seen consistently is that when we talk about a specific address in memory, that address only stores a byte or 8 binary bits. And we know that things like integers usually take up, right, 4 bytes, meaning 4 different byte groups, or a total of 32 individual bits, right, 32 ones or zeros. So to store an integer value in memory, it takes up 4 slots, right? Because each slot only stores 1 byte or 8 bits, and the integer itself is 32 bits, or a total of 4 of those bytes back to back. But everything revolves around the idea of a byte, but the nice thing is that we can think about the file itself as an array, where the byte numbers would be the index numbers. Because what we're going to eventually see is that not only can we think of the data as being organized in its binary form, but we can also go directly to a certain value in the file without having to go and visit everything that came before it. So we'll see, in other words, that you can treat the file itself like an array, because an array we know is a random access type of structure, meaning you can randomly go to any location in the array as long as you provide the right offset number. And that works because all the elements in the array are stored back to back in memory. Similar idea with the file, right? We know that the individual bytes are stored back to back. So as long as we know which byte we want to go to, then we can go directly to that byte without having to visit all the bytes that come before it. And so we'll see how, in that sense, the file can be treated like an array. So the file itself, really the way that we want to think about it is in terms of binary, right? So we have all of these different bytes in the file, depending upon what we're actually storing in the file. And so when we talk about things like a read operation, really what it comes down to is, first, how many bytes do you want to read? That's going to certainly depend on what you're actually trying to do. For example, if we're storing a number in the file, and that meaning what we think of as a number that's going to be stored, for example, in a variable of type int in the C++ program, well, then that means we're going to need to grab a total of 4 bytes, right? If we're going to be reading this into an integer type variable in C++. Whereas if maybe we're storing a character, like the character capital A, which is 8 binary bits, because we only need a byte to store a character, then that would mean that we're grabbing only 1 byte or 8 bits and reading that into a variable of type char. So how much we grab depends on what type of data we're working with. But the general idea is that when we talk about a read operation, we're talking about reading data from the binary file into some variable, right, in our program, which could be an array, or it could be a standalone variable, or it could even be a structure object for that matter. And then when we talk about a write operation, we're going in the other direction, right? We're going from memory to the binary file to write it into the binary file. But what it comes down to is the issue of bytes, right? That's what everything is going to ultimately come down to. And so what we're going to see is that we do in general handle reads and writes differently when a file is in binary mode compared to ASCII text mode. But the idea is that we have functions write and read, and we'll start to see some code examples with those. And with those functions, we specify a couple of arguments. One is for example, where are we reading from, right? And where are we writing to? So for example, with the read function call, we're going to be reading from wherever we're currently at in the binary file. And we'll talk about the issue of the file position and how that's going to be changed. But you're reading from wherever you're currently at in the binary file. But the 2 arguments are for, number 1, the variable that you're going to be reading it into, meaning in your C++ program. And then also the second argument is how many bytes. So everything, as we'll see here, comes down to the issue of bytes and grabbing the right amount of bytes. Because when you talk about reading from a binary file, really it's a couple of things that it comes down to. Number 1, how many bytes are you going to grab? Number 2, where are you going to start grabbing those bytes from? And we can control that, right? We can control how much we read from the file and also which portion, right? So if we have, 100 bytes in the file, we can go to one specific byte and read that 1 byte, or we can go to one specific group, for example, of 4 bytes and read only those 4 bytes, and that's it. So we can do whatever we need to do because of the fact that the file itself can be treated like an array, where you would think of it as the first byte is index 0, the second byte is index 1, the third byte is index 2, and so on and so forth. So you can, in some sense, right, think of it as like an array type of organization where the byte numbers themselves are the index numbers that you're going to ultimately work off of. But we'll see several new functions here. And the first thing is when you open the file, we have to set the mode. So we previously talked about things like the ifstream object or ofstream object. We know that those objects only can be used to do one or the other, but not both read and write. So ifstream, for example, can be used to read from a file, but not write. And then conversely, ofstream can be used to write to a file, but not read. But we do have a third option available, which is just fstream without either I or O before it. So just fstream, which is also the name of the header file that we include for files. And that type of object can be used for both reading and writing. So, because sometimes that's going to be convenient as well. If we might want to work off of just one file object, but potentially use that same object for things like both reading and writing, we can do that. And the idea is that when you open a file, in addition to specifying the name of the file, you can also specify what are called flags. And we'll look at a few of the key ones, but those flags control how you're choosing to process the file. And one of those flags is the binary flag, which is how you signal that you want to treat the file as a binary file, right, rather than as a ASCII text file, which is the default. So we'll see that there's a flag for input mode. There's a flag for example, output mode. There's a flag for binary. And then another flag that comes up in some cases is append, right? So there's actually several flags, but those are four of the big ones: are in, out, APP, which is short for append, and then binary, which is how you signal that you want to treat the file in its native binary form or format. And then we'll eventually look at things like the read and write functions and so forth. But that's the starting point here as we start looking at and thinking about binary files. Is the first thing is that we have to actually open the file in binary mode if we want to process it as a binary file as opposed to a text file. We'll eventually see how these things will come into play with things like the read and write functions. But as a starting point, meaning when we actually open the file, in addition to specifying the name of the file, we can also specify those flags, which includes things like the binary flag for signaling binary mode. And so this is the syntax what we're talking about here with these flags. So meaning when we call the open function here, we can specify flags in addition to the name of the file. And so the syntax here is after the name of the file, we have a comma, and then here we're specifying the flag in for input mode. Because especially with the stream object, right, they can work with both modes, but we still need to specify all that. So here, if we say iOS in, so iOS is actually a class where these things are being defined. So the iOS : in means input mode. So meaning that this file numbers.dat, which is a data file, we can read from that file but not write to it. Now, if we wanted to be able to do both, then we would just put both of those flags in there. So here, we do, if we want to specify both flags, then what we do is we put this bar here, and then after that we can put another flag. So for example, here we're saying f object open, name of the file is numbers.dat, and then the two flags are iOS in and iOS out. So now it's opened in both modes, right? Both input mode and output mode. Now, if we want to also, because by default, it's not going to be in binary format, right? Binary mode. But if we want to specify that, then that's just another flag that we can add on as well. So, and so each of these flags will be separated by this vertical bar here. It's actually what we call bitwise OR, but we can just separate each of them with that. And so then we'll just have all three of them, with each of them being separated by one of these vertical bars. So this is iOS in, iOS out, and iOS binary. So now that we have the binary specifier there, that's what's going to make it official, right? As far as now, we're definitely going to process this file in binary mode as opposed to ASCII text mode. Without the binary, it's just going to be treated like an ASCII file, meaning like what we did before in chapter 5 and some of your previous assignments, which were all dealing with files in text mode instead of binary mode. So that's the starting point here as far as working with the binary file, is we have to make sure that that flag is there, that meaning that binary flag is there. So numbers.dat now is open in both modes, but it's also in binary mode. So that's the starting point. Now the file's been opened. So once the file's been opened, just like we did before, we can start to think about, well, how are we going to start reading or writing? That's part of it. The other part of it is because we said that the file itself is like essentially a big array. How are you going to control also what you read and what you write? Well, we'll eventually talk about things like the seek functions, which can be used to go to a certain spot in the file. But for now, we'll look at the read and write functions. So the function for actually reading from a binary file is fortunately called read. So easy to remember, hopefully. But so we have a function called read for reading and a function called write for writing. But both of those functions have two arguments. Because in either case, you're going either from memory to the file, or you're going from the file to memory. So a variable is always going to be involved, right, with any type of read or write operation. It could be a standalone variable, or it could be an array, right? It just depends on what we want to actually do with our data here. And the second argument is going to be specifying how much, right, we're going to read in terms of bytes. Because we said before that your baseline is 1 byte or 8 bits. And so, for example, if you're maybe storing a character like the letter A, capital A, and maybe you want to read that into a variable of type char. Well, then in that case, you would just grab 1 byte of data from the file, meaning eight binary bits, and read that into your char variable. Whereas if it's an integer, then you would grab like 4 bytes. So how much you want to grab just depends on what it is we're working with. The second argument is where you're going to refer to the variable that either the data is going to be put into, right? If it's a read operation, reading from the file, putting it into the variable, right? Or if it's a write operation, then you still refer to the variable because that's going to be the variable that you take the data from and then use that to write into the file. But it's the first argument is a pointer, meaning an address needs to be there. And really with both the read and the write functions, the idea is that the type of the first parameter is a pointer of type char, meaning a pointer of character type. And the reason really is because we said before that the baseline is 8 bits or 1 byte, right? That's your baseline unit that you work with in binary is 8 bits or 1 byte. And that corresponds to type char, which is also 8 bits or 1 byte. And so the idea is that when you're working off of a binary file, right, regardless of what you're actually going to do in the end, we still want to think in terms of bytes. So that first parameter is going to be, the type is going to be a pointer to a character type, regardless of what you're actually reading, right? You could be reading a list of numbers that are going to be put into an array of integers, but it doesn't matter in terms of from the perspective of the read and write function, right? The type of that first argument is always going to be pointer to a character type because we work off of bytes as our baseline. So either we're going to grab 1 byte or we're going to grab multiple bytes, but a byte is nonetheless our baseline that we work off of. And so what it means is that if what we're doing is like reading a character from the file and reading that into a variable of type char, that's a pretty straightforward case. If we're wanting to do something like read into an array of integers, and there's going to be a little bit more that we have to say because we're going to have to ultimately cast it to type char star, because that's the type of the first parameter. But we'll look first at the version here that won't require casting. So if we're just wanting to do something like read a character into a standalone char variable, for example, then that's fine, right? We're not going to have to do any sort of cast operation for that. So what you would do in that case is for the first argument to the read function is you would just need to provide the address of that type char variable that you want to read into. So let's say in our program, we have a variable named C, right? A variable named C of type char. And so the idea is we have this binary file and we're assuming that there's a byte. Let's just assume it's the first value in the file. So we don't have to worry about going to the right spot in the file. So we'll just assume that the first byte, the first data value that's in the binary file is the character capital A, and then the goal is to read into the variable C, which is a variable of type char. Well, that statement is going to look like this then. So f object, and then the nice thing here again is the name of the function is just literally the word read. So f object dot read. The first argument is going to be the address of C, meaning the address of the char variable here. And now the second argument is going to be the number of bytes of the thing that we're reading into, in this case, the char variable. And again, in general, things can potentially take up differing amounts of memory on different systems. So it's not really the best idea to just put a hard-coded value there, because in C++ we have what's also called the size of operator, which can tell you how many bytes are, for example, of a certain type. So you can apply the size of operator to a variable that you've defined, or you can apply it to a type directly, like type int. And so what we can do here, since we know that we're reading into, in this case, the variable C, is the second argument can just be size of C, like that. So the end result of this, again, assuming that we're actually storing that character capital A, and when we say storing the character capital A, we mean storing it as a binary number, right? So there's a specific binary sequence, meaning a sequence of 8 ones and zeros that represents what we think of as capital A. And that comes down to the ASCII code table, which we'll look at a little bit next time. But that's what we mean when we say the binary file is storing capital A. So it's actually storing everything, it's storing as binary, but it's storing the binary sequence that corresponds to capital A. So assuming that's the first value that we have in the file, if we do this read statement here, then the end result is that now the variable C, that char variable, is now storing the letter capital A. So if we did, for example, C out C, you'd see a capital A. Now, we can certainly do things that are more involved in this. This is just kind of a starting point example, but we'll eventually look at things like how could you, like we mentioned before, how could you read several bytes in one go and populate the array from that, or even read several bytes into a structure object. So we'll look at those examples as well, but that gives us an idea for now of an example of what the read function is going to look like. And then as we continue this on Wednesday, we'll also look at things like the write function, and then we'll look at some of the more involved examples dealing with things like combining binary files with arrays, structures, and things, even linked lists. But for now, we've seen that the first thing is that we need to have that flag binary when we open the file. And we've seen at least a little bit of the idea behind the read function, but we'll look at several more examples on Wednesday when we continue our discussion here on binary files. Okay, but we'll go ahead and wrap up the lecture there for today.